Dear student friends, in last lecture we have seen the Huckel's rules of aromaticity and the applications of Huckel's rules. So we have clear the idea of aromaticity. The first aromatic compound in organic chemistry is the benzene. So there are various controversies about the structure of benzene molecules. So first of all, we will see the concept around the benzene. In 1825, benzene is first isolated by the Michael Faraday. It is the simplest and ideal molecule to illustrate the electronic delocalization. Resonance and aromaticity in the 1816s, chemists were provided some proposed structure for benzene, but these structures were not correct. Matcher list shows that the benzene has carbon hydrogen ratio 1:1 and the molecular weight of the benzene is 78. From this information, he derived the molecular formula of benzene for C6H6. For many years, chemists puzzles over the structure of benzene. Although they propose the number of structures, none fit the experimental data. In 1865, Alexander Braun suggested that benzene contains multiple bonds. Early 19th century, based on the molecular formula C6H6 and molecular mass 78, chemists represented the following different structure for the benzene. Lederberg structure of benzene. Lederberg benzene, now called prism because of prism shape. It is isomerizes to the benzene when isolated at 90 degrees Celsius. Next is Dewar structure of benzene. Dewar benzene is a cyclic isomer of benzene with the molecular formula C6H6. However, he did not propose it as the structure of benzene. Next is a Kekulé structure. Kekulé structure of benzene. The correct structure of benzene is proposed by Friedrich Kekulé in 1866, which contains multiple bonds. Friedrich Kekulé in 1866 proposed a planar hexagonal ring structure for benzene containing alternate single and double bonds. According to Kekulé structure first, benzene should undergo electrophilic addition reaction as like other compounds containing double bonds, but it doesn't. Instead, it undergo electrophilic substitution reactions. So these reactions can be explained over here. So according to Kekulé structure first, undergo electrophilic addition reaction like compound containing double bonds. It doesn't instead. So this reaction is given over here. Next is another problem with the Kekulé structure. It is a 1,2 disubstituted benzene should exist in two different isomer first and isomer second. So here, but doesn't exist isomer second. The two substituents would be present on the carbon which have the double bond between them. On other hand, expected isomer third, the two substituents would be present on the carbon which have a single bond between them. But in real life, benzene react with to form only one substituted structures. Resonating structure of benzene. In presence of this, Kekulé proposed a second structure for the benzene, that is fourth structure. The associated with the structure first, the second structure was also 6-member carbon containing with 3 single bonds and 3 double bonds, but in these structures. the single bonds and double bonds change places. He suggested that this oscillation was continual and took place so fast that two isomers could not be isolated. Thus, to explain this, Kekulé proposed delocalization of double bonds with the rings. So, as illustrated over here. Resonance structures of benzene. To show the benzene is a resonance hybrid, chemists usually represent the benzene with a circle in the center instead of drawing the individual double bonds. This hexagonal with a circle inside indicates the delocalization of the 6 pi electron within the molecules. So this is the resonance hybrid structure of the benzene given by the Kekulé. So on the basis of resonance, benzene is believed to be a resonance hybrid of the number of various canonical resonating structures. All these structures are canonical forms of the real structure of the benzene, and actual benzene is resonance hybrid of all these Kekulé structure. First, second are more stable than contributing 80% towards the resonance. So these are the resonating structure of the molecules. Next is the molecular orbital picture of the benzene. The best description of the benzene structure is given by the molecular orbital theory. According to molecular orbital theory, benzene is a planar ring that exists of 6 sp2 hybrid carbon atoms. Each of these sp2 hybridized carbon atom possesses unhybridized p orbital. Because of the planar structure of the bonds between the carbons, the partial p orbital of each carbon atom overlap with the unhybridized p orbital of its two adjacent carbon atom. This overlapping of p orbital creates a set of 6 pi electron orbital that involves all the carbon atoms in the rings and results in the delocalization of 6 available carbon electrons over the entire rings. So as illustrated in the figures. Then, so this is the molecular orbital feature of the benzene. It clearly indicates that each carbon sp2 overlap with adjacent carbon to form a sigma bond. Again, one of the sp2 hybrid orbital of the carbon atom is overlap with the hydrogen to form the sp2s sigma bond. So on a hybridized p orbital which is present on the each carbon atom get laterally overlap with the another carbon p orbital to form the pi electron cloud above and below the benzene rings. Hence, the benzene molecule is a most electron dense molecule and it is susceptible for the electrophilic substitution reaction and not for the addition reactions. Then next point is properties of benzene. So this is the structure, as the structure indicates that the carbon form the sp2 sigma bond with adjacent carbon atom. One of the sp2 hybrid orbital get overlap with the hydrogen to form sp2s overlap to form a sigma bonds. So next is this is the pi sigma skeleton of this molecule. The bond angle between any bonds in the benzene is 120. So the bond length between all the carbon atom in the benzene is 1.36 angstrom unit. So which is intermediate between the bond length of carbon-carbon single bond and carbon-carbon double bonds. So this clearly indicates that all carbon atoms in the benzene molecules are same. So the evidence of the delocalization of pi electron within the molecules is confirmed. Next is the properties of the benzene molecule. The 6 electrons of the benzene rings are freely moving, allowing the uniform distribution of electrons over all 6 carbon atoms and are called delocalized electrons. This delocalization decreases the energy and hence imparts the stability of the benzene due to this benzene having following characteristics properties. Number 1. To preserve delocalization, aromaticity and stability, benzene resists the addition reaction undergoes substitution reactions. Number 2. Further, due to the presence of pi electron cloud over the benzene ring, it is electron rich, it acts as a nucleophile, hence undergo electrophilic substitution reaction. Thank you. So with this we have completed these things. So thank you very much. We will see the next topic, that is reactions of aromatic compounds, in next